So it will be important for applications of deMoivre's theorem to be aware of two main things. First of all, expanding the binomials, and secondly, there's an identity about z plus 1 on z. So let's first have a look at the expanding the binomials. Expanding the binomials, I've written up the top here the general expansion that you would have seen from extension 1. Notice that if it's to the power of n, it starts nc0, then nc1, nc2, all the way up to ncn. Have a look at the general term, nck. See the power of b is now k, and see how those two powers add up to n. So that's the general expansion of a plus b to the power of n. So, for example, a plus b to the power of 4 would be 4c0, a to the 0, b to the, a to the 4, b to the 0, these two being the same. And then 4c1, a to the 3, b to the 1, and 4c2, a to the 2, b to the 2, 4c3, a to the 1, b to the 3, and 4c4, a to the 0, b to the 4. So I just keep getting these little numbers the same here, the bottom one and the final power the same. These two always add up to 4. And it just goes 4c0, 4c1, 4c2, 4c3, 4c4. When you go to Pascal's triangle, or you get on your calculator and use the C button, you can work out 4c0 is 1, and 4c4 is 1. And then 4c1 is 4, and 4c3 is also 4, and 4c2 is 6, and of course b to the power of 1 is just b, and a to the power of 1 is just a. So that would be your a to the naught is 1, b to the naught is 1. So that might be what the expansion of a plus b to the 4 might look like. So that's the first thing that we need to be able to work with, binomial expansions. The second thing that we need to know about is the identity z plus 1 on z and z minus 1 on z if z is equal to cos theta plus I sine theta. So one thing you could tell me about that straight away is that that has a modulus of 1. So it's representing all the points on a circle 1 unit away from the origin on the complex plane. But it has a modulus of 1, but for the purposes of what we want to achieve here, that's fine. So we want to show that z plus 1 on z is equal to 2 cos theta, and z minus 1 on z is equal to 2 sine theta I. This is equal to 2 cos theta, and this is equal to 2 sine theta times I. Well, z plus 1 on z here would be the same as cos theta plus I sine theta plus 1 on cos theta plus I sine theta. That's z plus 1 on z. Now, we normally realise the denominator when we have a fraction here with a complex number in the bottom there, if it's got the imaginary part. So let's do that. Times that by the conjugate. So I'm just timesing that second part by 1 because anything divided by itself equals 1. So this will be equal to cos theta plus I sine theta plus cos theta minus I sine theta over, and normally that's a plus b, a minus b is a squared minus b squared, but when I is involved, we're going to have an I squared, which is minus 1, so it'll be a squared plus b squared. So I'm saying it'll be cos squared theta plus sine squared theta. And we know that cos squared theta plus sine squared theta is 1. So basically the denominators disappeared there, and we have this situation where my I sine thetas, one's positive, one's negative, they cancel, leaving me with 2 cos thetas, which is what I said up the top here. Z plus 1 on Z is 2 cos theta. So what about Z minus 1 on Z? Why is that 2 sine theta I? Well, it's the whole same process. If I make this a minus, then this is a minus. This is a minus. And then when we subtract this top line, notice that this bar here is a form of grouping symbols. So the minus is outside these grouping symbols. So it's minus cos theta, and minus of a minus will actually be plus I sine theta. So cos theta minus cos theta cancel, I sine theta and another I sine theta, there's 2 of them. So there's 2 sine thetas times I. So that's where I get Z minus 1 on Z is equal to that. So that's an important identity, but it's actually taking it one step further that's particularly important. And that is, assuming Z is cos theta plus I sine theta still, I want to know what Z to the n plus 1 on Z to the n is worth. That's the important thing. So that'll be cos theta plus I sine theta to the n plus 1 on cos theta plus I sine theta to the n. That's what's going to be important to me here. So using deMoivre's theorem, that would be cos n theta plus I sine n theta over 1 over plus 1 over cos n theta plus I sine n theta. Once again, we realise the denominator by multiplying by the conjugate minus I sine n theta on cos n theta minus I sine n theta. So we end up with cos n theta plus I sine n theta plus cos n theta minus I sine n theta. And the reason is because this will become cos squared n theta plus sine squared n theta, which is 1. Cos squared n theta plus sine squared n theta equals 1. And as before, that and that will cancel, being opposite in sign. So we have 2 cos n theta. If I did the same process, but decided to make it be a minus, that will be a minus, that will be a plus, no longer cancelling them, but instead adding the signs together, and I would get 2 sine n theta I, if it was a minus. So just to put that together for you as something that you should know and be able to work with, we've done expanding the binomial as an important thing you need to have, and also you need to know that Z plus 1 on Z to the n is equal to 2 cos n theta, and Z to the n minus 1 on Z to the n is equal to 2 sine n theta times I for us to now be able to work with applications of deMoivre's theorem.